Hello, I'm Raskin and I will be telling you about giant components in random temporal graphs. Sorry that I cannot do it in person. This is of course presenting our joint paper with my, rather numerous colleagues. First, in which context can temporal graphs arise and what is the intuition behind them? Consider that you want to do some aerial photography and you are using a drone to do the photos. Sorry, a small correction. You are using multiple drones to make the photos. You probably want some amount of communication and coordination inside your drone flock. Unfortunately, of course, not all drones can reliably communicate to each other. Maybe even if you are working over a large area, it's only a few drones at every moment that actually can communicate. On the other hand, if you hope that your drones will execute some coordinated action, you don't need them to communicate instantaneously. It might be enough if the data is relayed between the drones over multiple hops. So when we model it, we can create a node per drone, and then we create an edge, temporary edge, when the drones have a usable connection between them, and then we study where we can relay the data, so which sequences of this edge at this time are usable to relay the data. So technically, a temporal graph is a graph where each edge has some presence times when it can be used. And a temporal path, also called journey, is a sequence of edges and times when the edges are crossed, so that the edges are available at these times according to the labels in our temporal graph, and the times are also increasing along the path. So, for example, A, B, C, G, D is indeed a temporal path, as the times on the edges are increasing. We don't have any choice for each of the edges, but at the same time, A, C, D is not a temporal path because the edge AC has to be crossed later than the only time the edge CD becomes available. One could ask whether ACED is a temporal path, as AC and CE have the same time, 4. It depends on the definition. We can require strictly increasing times along the path, or we can allow non-strictly increasing sequence of times. It doesn't matter for our model because with probability 1, all the times are unique. The notion we care about a lot is temporal graph reachability. We say that the vertex V can be reached from the vertex U in a temporal graph if there is a temporal path or journey from U to V. Temporal reachability has some interesting properties. For example, unlike the reachability in undirected graphs, and we don't have directions on our temporal edges, temporal reachability is not symmetric. So, for example, if we have 3 vertices and 2 edges, AB and BC, and AB is available only at time 1 and BC is available only at time 2, then we can reach C from A, but we cannot reach A from C. Moreover, unlike the static non-temporal graphs, even unlike directed static graphs, temporal reachability is not even transitive. In the same example, we can reach B from C and we can reach A from B. But as we reach B too late to continue to A, we still cannot reach A from C. And in general, lack of transitivity means that a lot of basic and obvious facts about the static graphs do not have an alex for the temporal graphs. For example, if you have a sink, which can be reached from everywhere, and if you have a source from which you can reach all other vertices, and you can even reach the source from the sink, it is still not enough for strong conductivity in the temporal case. And in general, you should not always translate your graph intuition, and you should probably just think in terms of journeys. You change from one bus to another. Our model is a random simple temporal graphs, or temporal Erdős-Rényi graphs. We just take the same parameters and NP, the number of vertices and the probability of presence of the edge. We take an Erdős-Rényi random graph, and we take a uniformly random permutation of the edges that are present. So we pick a random strict edge order on the graph. And we have studied already this model before in terms of basic connectivity. So before log n over n, for two given vertices, there is probably no temporal paths between them. Afterwards, most pairs have a temporal path. At 2 log n over n, the first source arises, and most vertices become temporal sources. And at 3 log n over n, the graph becomes temporally connected. And in the current work, we study the connected components and their size. For context, in the static case, or you can say for the footprint, so for the set of the edges present in the temporal graph, at the density p equal to 1 over n, we already have a linear size connected component arising. But in the temporal case, we cannot hope for it, because before density log n over n, a random pair of vertices is not yet connected. And on the other hand, at the log n over n, the earliest we could hope for it, we get a linear size connected component arising. Moreover, it immediately grows to the size n minus small o of n. So overall, if we merge together the timeline for connectivity and put the connected component on this timeline, we get a picture like that. So how do we define formally a connected component? Obviously, the intuition is that every vertex in the connected component can reach every other vertex there. But when we can say can reach, do we consider the temporal paths inside the connected component, or do we allow to leave and re-enter the component? In the static case, for normal paths, it is irrelevant, because if B is reached from A via C, then C can reach everyone B can reach, C is reached by everyone who can reach A, and therefore C can be included into the connected component. However, without transitivity, we do get two different notions. So there are open connected components where you are allowed to leave and re-enter, and there are closed connected components where everyone can reach everyone via temporal paths which lie strictly inside the connected component. However, in our model, the sharp threshold for appearance of linear size components coincides for the open and for the closed case. The proofs, however, are a bit simpler for the open case. The basic idea of the analysis can be illustrated by a picture like this. Our goal is to exclude a small minority of vertices which are not in the connected component, and then for each pair of the remaining vertices we want that there is a temporal path from one to another. To prove this, we use that our edges are already ordered by the time of appearance. So we consider separately three phases. The first phase includes the earliest by appearance third of the edges. The last phase includes the latest by appearance third of the edges, the first third. And then there is the middle third. And we study separately what happens in each of the phases. In the first third of the time, a typical vertex can reach a bit more than cube root of n other vertices, and atypical vertices that cannot are not included in our components because they are few. The last third is actually symmetric to the first third, but in the reverse time. We want that every typical vertex is reached by a bit more than cube root n other vertices, and again we exclude the atypical ones. In the middle phase, we find out that any two large sets of vertices are connected. In particular, everything that is reached from A and everything which can reach B in the corresponding first and the last third. And this is preserved even though we have lost some edges because they are used up in the first or the last phase. If we rescale the time so that by time p we have density p of edges already having appeared once, then normally for a pair of vertices it takes time log n over n to establish connectivity with O of log n hops. However, it is possible that a vertex has no new edges even though a lot of the edges appear elsewhere in the meantime. And the longest observed sleeping time is basically log n over n. Basically, this sleep defines this extra log n over n for each level of generality and connectivity. So for a typical pair, you have log n over n time for one to reach another. For a vertex to become source, to reach all the vertices, you need an extra log n over n. And so that all vertices become sources, you need yet another third log n over n. But this matters if you want generality. If you just care about a supermajority of the vertices, well, most vertices do not sleep and they form a connected component and even a closed connected component. Another piece of analysis is the notion and the algorithm of the foremost tree. This is pretty similar to Dijkstra's algorithm. You basically just look for a vertex, what it can reach, and you take the earliest edge which enlarges the set of the vertices that can be reached. And the same algorithm can be run in the reversed time. So we can ask what can be reached from A, and we also ask from where A can be reached. To explain a bit more what I was talking about in the rescaling on the times corresponding to the random ordering, the Erdős-Rényi temporal graph is defined with random edge order, so you can say that the times are integers. Of course, you can rescale, and if you take for your edges uniformly, randomly, and independently time labels from 0 to 1 or from 0 to p, you get, with probability 1, unique time labels, and you get uniformly random ordering. And another way to get uniformly random labels in 0 to p is to take uniformly random labels from 0 to 1 in a click, and then remove everything after time p. So this gives us yet another point of view on the situation. If you take a click and you change the p, which is a cutoff for removing the edges, when a giant connected component arises. To say at least a bit about the closed components, well, the construction is kind of similar to the open case. The basic three phases are preserved. However, in the very beginning and in the very end, we need a bit more edges and a bit more time. In these small subphases, a chosen vertex quickly reaches a polylogarithmic number of other vertices without going through the excluded ones. And once you are starting from a polylogarithmic number of vertices which are already reachable, the further growth has very good concentration. So for the conclusions, in the random simple temporal graphs, in Erdős-Rényi temporal graphs, a giant connected component arises approximately as soon as vertices become connected in the typical case. There is a sharp threshold between the maximum connected component being small o of n and maximum connected component being n minus small o of n, containing almost all vertices. And we have developed the techniques for various tricks in the multi-phase analysis of temporal reachability. Thanks for your attention, and I hope we have a way to answer questions.